Alright, this time this is the Tutor Wizard, and what we're going to do is we're going to do a bunch of linear transformations. Basically what I'll do is I'm going to give you the definition of what a linear transformation is, check a couple linear transformations, try to find the standard matrix of a transformation, and then look at a couple clever ones on weird abstracts, more abstract spaces, which I like, and verify that they actually are linear transformations. I'm going to call V a vector space. If you're using regular linear algebra and you don't want to do the abstract stuff, the vector space is some copy of Rn. Otherwise, it could be some other weird vector space. So let V and W be vector spaces. A transformation from V to W is a rule that assigns to any vector V inside V a unique vector W from W. Basically, this is the same thing as what we're describing of what a function is. A transformation transforms things from one vector space to another vector space. Regular for functions, what you're going to do is we write it like this, and you're transforming one dimension to one dimension, and our vector space will be R every time, so we're transforming. This is what we mean generally about what a transformation is. So this is just what a transformation is. They're moving things around in space. We call V is, this is usually denoted T from V to W. And then when we have these, what we're going to say is T of V is equal to W. So for every vector V in V through this transformation, we can define another guy, W, who is the image of V under T. And this is our notation. We call V the domain and W the codomain in most cases. Among all of the transformations, we want the definition of what linear is. Those are the ones that are well behaved and are useful to us. So we want to, out of all transformations and moving things around, what does it mean to be linear? We want what a linear transformation is. A transformation T from V to W is called linear if I'm going to phrase it as two axioms. You can show that this in a theorem, that this is if and only if we're logically equivalent to having one axiom, which is slightly lazier, and they jam it all together. But as students at first, you definitely want to check the two conditions of one, T of U plus V. This U and V are inside V. If I add them in V and then apply the transformation and then send them somewhere, where is that somewhere? That's the same as sending it to T of U plus T of V. So you can split sums essentially. And if you scalar multiply things in V first as a vector space, you're allowed to. What happens to the scalar? If I take T of KV, this will be K times T of V. So you basically, what that says is you can split sums in your transformation and you can spit out scalars. If you can spit out the scalars, some of the books will write this as one axiom, which will say that T of alpha U plus beta V is equal to alpha T of U plus beta T of V, which is saying they're just writing it as one axiom. You can prove that this is logically equivalent to this one statement, so you can view them as the same thing. I choose this one at first so you can check conditions one at a time. And then we have a result or a baby theorem, which gives us a third condition, which usually we'll start writing first. If you are a linear transformation, and this is important at first, we're going to try to keep the abstraction down, but the 0 in here is different from the 0 in here. They're both vector spaces, so they both have a 0, but they may be different things. So if t is linear, then t of 0 v, the 0 in this vector space, is the 0 in W. 0 maps to 0. When it's in dimension, it says that 0 will map to 0, but if we're in different dimensions or the vector spaces are different entirely, you'll see in a couple of my examples, the 0 may not be the same guy in each vector space. So basically this is awfully similar to subspaces. Subspace conditions have, you are a subspace of a vector space V if you have closure of addition. So an addition condition, if U and V are in the subspace, then U plus V is in the subspace. Now we have a condition for a linear transformation. If T is a linear transformation, it splits sums. It has a sum condition. For subspaces, you have to have closure of scalar multiplication to be a subspace. And for a linear transformation, we have an axiom about scalars. You have to spit the scalar out of the linear transformation. And then for subspaces, we also have a condition that says if you are a subspace, 0 is always in the subspace. We have a condition about 0. And we have a condition about 0 for a linear transformation. 0 has to map to 0 if it is a linear transformation. So this condition is the easiest way to show that a transformation is not linear. If 0 doesn't go to 0, it's not a linear transformation. You don't have to check any other axiom. This is the easiest one to check right out the gate. But some nonlinear transformations do still send 0 to 0, so you can't just say, oh, it went to 0, so linear. But if it's not 0, let's rephrase the contrapositive of that statement of how you would want to use it. If T is linear, then T of 0 equals 0. This is logically equivalent to the contrapositive statement, which says the negation of this implies the negation of this. Long story short, that says if T of 0v is not equal to 0w, if 0 doesn't go to 0, then T is not linear. And this is how you would want to show a transformation is not linear first. Always see if 0 maps to 0. If it doesn't, you're done. It's not a linear transformation. Let's check these conditions on a couple of linear transformations. Also, most of the books, what's the difference between an operator and a transformation? Nothing, except an operator goes from the same dimension to the same dimension, or from the same vector space to the same vector space if you're using more abstract ones. So we call a transformation an operator if it operates on that vector space. Let's give two quick examples. Let's look at example 1. T is going to go from R2 to R3. I'm going to go up a dimension. So this is not an operator. This is transforming 2 space into 3 space. It's blowing up a dimension. And we're going to say that T of the best way, this is also notation, this is the problem a lot of the time. I'm going to describe just like I would with f of x. If f of x is x squared, then that's what you do to it every time. We're going to have to do the same evaluation type thing with linear transformations with more than one coordinate now, which is confusing at first, but you just put x plus y wherever x was in the expression. So let's describe it this way. T of x1, x2, there's a vector in R2. If I now hit that with T, that's going to send me to a 3-dimensional vector, which is going to be, I'm arbitrarily going to make it up right in front of you. Let's go from x1 plus x2. The first coordinate is those guys. Then let's go to 0, and then let's subtract those coordinates, x1 minus x2. So I just blew up in a dimension, and then now I'm going to see if this is a linear transformation. Let's check. The conditions I want to check first, I'm going to reorder those conditions. First of all, I want to see if T of 0 equals 0. I want to check to see if T of u plus v is equal to T of u plus T of v, question mark. And I want to see if T of a scalar times u is a scalar times T of u. You can call them u and v and x and y, it doesn't matter what you call them. We're going to see if these 3 things happen or not. I list this one first now because that's the easiest one to check. If that one fails, you can say not a linear transformation. You don't have to check anything else. If that is 0, we keep going and check all of them. T of 0 is equal to, who is the 0 in dimension 2? 0 for R2 is the vector 0, 0. And so that says that will be T of 0, 0. And where does that send me? It sends me to 0 plus 0, 0, 0 minus 0, which is luckily 0, 0, 0, who is the 0 in R3. So T of 0 went to 0. Check. The next axiom, every time we do this, just like subspaces, I need two vectors in there. We're going to add two of them, and we're going to scalar multiply one and see if we can spit them out and split the sum with the linear transformation. What that means is you should always take two vectors in R2 and prep them and then add them and then scalar multiply them and see what they look like. Axiom 2 said I'm going to have to add them. So what does u plus v look like in R2? U plus v is going to equal u1, u2 plus v1, v2. And I know how to do that. That's coordinate wise. So we add that u1 plus v1, u2 plus v2. The same thing's always going to happen for condition 3. So let's prep that condition 2. K times u, and every time it doesn't change. Change the numbers. Is going to be k times u1, u2, which is coordinate-wise scalar multiplication, ku1, ku2. Every time we do this, I need to know what u plus v looks like in whatever vector space v I'm in. And I have to look at ku. And now what we're going to do with those is apply t to them and see what happens. Can I split the sum and can I split the scalar out? Turns out in this case, yes. Now we need t of u plus v. That is t of u1 plus v1, u2 plus v2. What does that do? It does this thing, but I have to put those wherever x1, x2 was now. This gives me u1 plus v1 plus u2 plus v2, 0. u1 plus v1 minus u2 plus v2. Now we have to see the definition of its addition in reverse. Doing this was easy, but can you split it? That's what I'm going to do with this now. I'm going to group everything together. From here, this equals u1 plus u2 plus v1 plus v2. 0, I'm going to cheat and expand cleverly, is 0 plus 0. And then this one is u1 minus u2 plus v1 minus v2. And now can you see that that's the reverse of this vector plus this vector, which is going to be u1 plus u2, 0, u1 minus u2 plus v1 minus v2, 0, v1 minus v2 plus, I caught it. Who are those guys? T of x is this, so this is T of u. And what's this? T of v. So it did split sums. T of u plus v is T of u plus T of v. The third condition, I'll rewrite it again. K of u is ku1, ku2. So now I'm going to apply t to that. That says t of ku has to equal t of ku1, ku2. What does t do to a vector? This. So it sends the first coordinate plus the second coordinate. ku1 plus ku2, 0, ku1 minus ku2. And what you have to see is in reverse. Can I pull k out of each of those? Yes, because this is 0 is k times 0. So I'm going to write that as k u1 plus u2, k times 0, k times u1 minus u2, which is equal to k times u1 plus u2, 0, u1 minus u2, which is what? T of u. That says 0 maps to 0. This transformation splits sums and it spits out scalars. Therefore, T is a linear transformation. this definitely is a linear transformation. Now let's reverse it, and we will switch these around and go from R3 down to R2, and we'll find one who's not a linear transformation. It doesn't matter what dimension you're in. Now we're going down, so I'm going to go from R3. So now we're taking vectors in R3 and reducing them to projecting down into R2. What are we going to do with these vectors? Let's say that T takes a vector x1, x2, x3, and that sends it to the vector 1, x1 plus x3 minus x2. I didn't even have to use all the coordinates, but it doesn't matter. This is not going to be a linear transformation. Probably not even in the mood we'll see, but 0 doesn't map to 0, so then we're done. Should I even check the other conditions? Maybe. We'll see. You do it. Axiom 1 I always start with. T of 0 is T of 0, 0, 0, because that's the 0 in R3. And what does that say that that's going to go to? It's going to send it to 1, 0 plus 0 minus 0, which is the vector 1, 0, who is the vector I. But it doesn't equal 0. So 0 didn't map to 0. T is not linear. When you try to do scalars and adding, you should try this on your own. I'm not going to do it. I'm going to do the more fun ones from my point of view, the abstract ones. But when you try to scalar multiply, the k will go onto here, and now it'll be a k, not a 1, so you couldn't split this. And then when you have to split a sum, you would need a 1 for both of them, but you only have one of them, so you can't split the sum either. You would need a 1 plus 1, which is 2, which you're not going to get, so it fails all 3 conditions in this case. This is not linear. Now, to wrap up, let's do a couple more clever ones. Let B equal C1 AB be the vector space. Oh, disclaimer, I'm assuming you have some calculus knowledge because we're going to do calculus. Derivative and integral are linear transformations on the space of all vector space of differentiable functions to continuous functions. So let V be the space, vector space of all once differentiable functions. So continuously differentiable functions. And let W equal C0AB be the vector space of all continuous functions on the interval AB. So V is differentiable and W is continuous functions. I want to look at D, which we are going to go from C1AB into C0AB, which is D is the derivative with respect to X of function F that's going to be in our space. So D is the derivative operator. What we want to show is that this is actually a linear operator. Let F and G be in C1AB, which means their derivatives exist and are continuous on the interval AB. We're also going to take a K and R, and what are the things that I have to know? Who's the 0 function? The 0 function is 0 of x equals 0 for all x. So we have to check this, but what is the derivative of 0? What's the derivative of any constant? The derivative of any constant is 0. So D does send the 0 function to 0. This looks weird because it's sending the 0 function to the 0 function, which is the number 0 consistently across. But check. 2. If I take the derivative of 2 functions, can I split that? That is by definition the derivative with respect to x of f of x plus g of x, which is the derivative with respect to x of f of x plus the derivative with respect to x of g of x, which is equal to df plus dg. So it splits sums, definitely. And third, if I have the derivative of k times a function f, this is the derivative with respect to x of k times my function f of x, which is k times the derivative with respect to x of my function x, which is k d of f. So it spits out scalars. So the derivative operator from C1AB to C0AB is a linear transformation. Yeah, all right. Let's let V equal C0AB. Let's go on 0, 1. And let W equal R. Then the operator I from C0, 1 to R, which is I of f equals the integral from 0, 1 of f of x dx, is a linear operator, or not operator, linear transformation from C0, from continuous functions to the reals. Coincidentally, there is a little bit of machinery going on here that gets sort of whitewashed when we say these things, but there is a few big theorems that say if a function is continuous on an interval, then it is integrable. So we know that the definite integral exists on that. Every continuous function on a closed interval is integrable. Finding the antiderivative is another game. Those are different videos, but right now we know this exists and is well defined because we're going from all continuous functions, and if you're continuous on that interval, we know that the integral exists, and then it's computing a number, which is the area under that curve for that. So we're mapping from continuous functions to find out what their areas are. This is what the integral guy is actually doing. He's a linear operator. What do I have to check? I of 0 equals the integral from 0, 1 of 0 dx, which is 0. Check. What's the area under nothing? Nothing. 2. The integral I of f plus g is going to equal what? The integral from 0 to 1 of f of x plus g of x dx, which is, I'm not going to show, but you can actually split integral sums, so they're assuming you know calculus, and I can split that as the integral from 0 to 1 of f of x dx plus the integral from 0 to 1 of g of x dx, which is I of f plus I of g. So it splits sums. And what's the last thing I have to check? That this integral function or operator transformation spits out scalars. So 3, I need I of k times f to equal the integral from 0 to 1 of k of f of x dx, which we can pull out, which is k, the integral from 0 to 1 of f of x dx, which is k times I of f. So I is a linear transformation. Please subscribe below, hit the notification bell to get the updates for all the other videos that are to come. There will be many more linear algebra and calculus videos for the prep, especially for the midterms this semester.